Another type of discrete probability distribution that we see is called a geometric distribution. Geometric distributions also produce geometric PDFs. And just like binomials, there are four characteristics of interest, and three of them should look familiar. So the first is that there are only two outcomes. And we know we call those success and failure. The next is that the trials are independent of each other. The third is that the probability of success is the same for each trial. Right now, in your head, you're probably thinking this sounds exactly like a binomial distribution. And it's the last requirement that changes this. For binomial, we wanted a fixed number of trials. With a geometric distribution, the experiment continues until we obtain a success. So unlike a binomial where I know how many trials I'm going to do and I count the number of successes, here I keep running the experiment over and over and over again until a success occurs, and I'm keeping track of the number of trials it requires to get to my first success. So binomial is keeping track of the number of successes. Geometric is keeping track of the number of trials needed to reach a success. So a little bit different. The upside is there are shortcut formulas here, and our calculator can do the probabilities exactly the same way they did for for binomial. The difference is with binomial, we went straight to the calculator for probability. We actually have a formula for probability that's pretty straightforward. If I want the probability that my first success occurs on trial A, to calculate it, it's the probability of a success times the probability of failure to the A minus 1 power. And this rule comes from the multiplication rule. If I took A trials to get a success, that means I had A minus 1 failures, failure times failure times failure times failure, and then 1 success at the end times success. So this is just shorthand for what we would calculate if we were doing failure and failure and failure and failure and success. On the calculator, we're going to do exactly what we did for binomial. We're going to go second vars. Because we know that takes us to the distribution menu. And then on second vars, way down at the bottom, option E is, and it'll say Geomet PDF. And Geomet PDF actually only asks for two things, because we no longer have a fixed number of trials. It wants the probability of success, and it wants that trial number where the first success occurred. And that's pretty straightforward. If I want to find the probability that the first success occurred on trial 5, right, geomet PDF, whatever my p-value is, comma 5. The tricky part comes when we're dealing with a range of values. And we know that when I'm looking at a range of values, that means I need the cumulative distribution. So second vars, and then I want option F, which is geomet CDF. And just like binomial, geomet CDF only does the less than or equal to. This would be geomet P comma A. If I'm doing anything else, I have to modify the A, or I have to use the complement rule. It only does A inclusive. If I don't want to include A, I need to tell the geomet CDF function. Oops, I forgot to write CDF there. Sorry, guys. Oops. We'll try this again. If I don't want to include A, I have to tell the geomet CDF function to start with the value that is less than A. If I want to do less than 4, I need to tell it to start at 3, otherwise it'll start at 4. I know that if my arrow or my inequality points to the right, I have to use the complement trick, 1 minus, 1 minus, because my calculator only goes to the left. And I know both of these are geomet CDF because they're ranges. For x is greater than or equal to a, if a is included with the greater than, it should not be included with the less than. So we start with a minus 1 here. For x is greater than a, if it's not included with the greater than, it does need to be included with the less than. And that pattern's exactly what we saw with binomials. And remember, for homework and tests, you're allowed to use your notes, so you don't have to have this memorized. Let's do an example. We can see what this looks like, and then we'll talk about mean and standard deviation really quick. So this one says, a soda pop manufacturer runs a contest and places a winning bottle cap on every 6th bottle. If a person buys the soda pop, find the probability that the person will win on his first purchase, will win on his third purchase, or not win on any of his first 5 purchases. So first thing is we're keeping track of when he wins. That's keeping track of a trial number, so I know this is a geometric and not a binomial. I need to know my probability of success. If I'm putting a winning bottle cap on every 6th bottle, there's a 1 in 6 chance that I'm going to win, because the first 5 are failures, the 6th one gets a winning bottle cap. And then we're just going to work through the problem looking at what the probability notation looks like and which formula to use. So the first one says wins on his first purchase. P, win occurs on first trial, x equals 1. That's an exact value, so that's the PDF. So geomet PDF, and then I want probability of success, trial number where that success happened. So let's pull up our calculator and go ahead and do that together. So to pull up geomet PDF, we go second vars, maybe if I can type, second vars, and then all the way down to the bottom, and then 1 divided by 6th, comma 1. And so I get 0.167 rounded, or 16.7%. You'll notice that 1/6 is 0.167, and that makes sense. If the probability of success is 1/6, then I won on my first trial, I'm expecting that, yeah, it's just 1/6. The next one will look a little different. The next one says win on his third purchase. Px equals 3 occurs on a specific trial. So geomet PDF for exact value, 1/6, comma 3. So I'm going to pull the calculator up again. We'll go ahead and do that together. So second vars, no, not that one, second vars, there we go. Geomet PDF, and it's 1/6, comma 3, and we get 1/16. Or 11.6%. So there's an 11.6% chance that I'm going to get that winning bottle cap on my third bottle. I can check this another way. I know that this should be the probability of success, 1/6, times the probability of failure, 5/6, to the x minus 1 power. 3 minus 1 is 2. And if I run that, notice that formula gives me exactly what that calculator spit out. So that formula that we saw earlier also works for exact values. Last one. C says did not win on any of his first 5. So P first 5 fails. And this one, I don't think we want to use geomet. I think we want to use what we know about the multiplication rule. This is P fail and fail and fail 5 times, right? And fail and fail. And I know and, doing the same thing repeatedly, is a multiplication problem. So this is just P fail times itself 5 times. 1, 2, 3, 4, 5. And I know what the failure fraction is. If the success fraction is 1/6, the failure fraction is 5/6. So 5/6 times itself 5 times, which is just 5/6 to the 5th power. And we're going to do that on our calculator really quick. So 5 divided by 6 to the, why does that look so weird? To the 5th power, and I get 0.402, or 40.2%. So there's a 40.2% chance that my first 5 soda bottles are failures. They have a losing bottle cap. That makes sense because I know that the winning bottle cap is every 6th bottle. It makes sense that the first 5 failures are fairly common. In order to give us a reference for what's common versus what's uncommon with a probability distribution, we know we look at the mean and the standard deviation. So let's go ahead and look at those formulas. So for the geometric distribution, if I want to calculate the mean, it's 1 divided by the probability of success. So if I go back here, my probability of success is 1/6. That means my mean is the reciprocal of that, 1 over 1/6, which is just 6. On average, I expect my first win to occur on the 6th bottle, because every 6th bottle gets a winning cap. That makes sense. That's why our answer to C makes sense. It should be fairly common to lose the first 5 trials. The standard deviation is a little bit more complicated, but not a whole lot. We're still taking a square root, and it's the mean, 1 over p, times 1 over p minus 1. And that's something that we would do on a calculator. We're going to go ahead and do this really quick with an example, and then we will be done with week 2's material. So our example says 1 in 5 teachers stated that he or she becomes a teacher because of the long summer vacations. I can assure you that is not a good reason to become a teacher. It says find the mean and standard deviation for the distribution of teachers who say they became teachers because of the long summer vacation. So I know for both of those calculations, I need p, because the formula for mean and the formula for standard deviation involve p. So I'm interested in a success is defined as became a teacher because of the long summer vacation. And we are told that 1 in 5 do that. So 1/5 of teachers became teachers because of the long summer vacation. So our probability of success is 1/5, or 0.2. So let's go ahead and do these calculations. I know my mean is 1 over p, which is 1 over 1/5. This is a reciprocal, so I end up with 5. Our mean is 5. I expect to find the first teacher that became a teacher because of the long summers to be on my 5th trial. That's the average. My standard deviation, I need to do the square root of 1 over p. Well, I know 1 over p is 5, times 1 over p minus 1, 5 minus 1. So this is the square root of 5 times 4, which is the square root of 20. And we can do that pretty quick on our calculator. I get 4.47, which is pretty big compared to the mean. So this data is spread out about the mean. This has a really wide spread. All right, as per usual, if you have any questions, feel free to send me an email or drop by office hours on Tuesday or Thursday. Otherwise, I will see you in the week 3 videos.